Hi, in this video, we want to look at matrix multiplication. Matrix multiplication is very different from multiplication of numbers that we're used to, that we're familiar with. This is a very different process. So when I have a table of numbers, when I do multiplication on tables of numbers, it's actually going to be a mixture of addition and multiplication to get the numbers that are correct. Now, multiplication of matrices is going to be critical throughout this course. You have to kind of have an intuitive understanding of this to be successful going forward. Basically, if you don't get this section, the rest of the semester is sunk. We are going to be relying on this constantly. Okay, so what's going to happen is that I'm going to take a row, I'm going to take a column, and I'm going to combine them in a very particular manner. And in that combining, there's a lot of special mathematical and algebraic properties. So first thing I need to say is this is a row and columns operations. On the left, you're working with the row. On the right, you're working with the columns. Remember, it's always rows before columns. So if I have A is an n by m matrix, B is an m by p matrix, and we multiply A and B, so A times B, then what we're going to get is an n by p matrix. So n by m times n by p gives me an n by p matrix, like this. You can see it's not actually correct, but it's an easy way to think about it, to say that these things, the m's cancel out with each other, and that gives me the dimension I get over here. So if I multiply A and B together, A has n rows, m columns, B has m rows, p columns, then the product of A and B is going to have n rows and p columns. The columns on the left, that's A, must match the rows on the right, that's B. Okay, so what is our actual formula? The actual formula is, if I'm going to take, let's say it's C, is the matrix that comes from multiplying A times B in this order. Well, the entries, ith row, jth column, I'm going to go through, I'm going to take all the A's and all the B's. So all the A's with the row I, all the B's with column J, and then I match up that middle index. And then we add it all up. This sigma means addition. Hopefully you know that. All right, so let's look at an example. I'm going to take A and B, I want to do multiplication. So when I take A times B, remember it's rows and columns. I've got to take the first row and the first column. I'm going to combine these in a very particular manner. I've got 1 and 9, 1 and 9, 3 and 8, 3 and 8, 5 and 7, 5 and 7. Now, with each of those pairs of numbers, we do multiplication, and then I add the multiplication. Okay, so first row, first column gives me the entry in the first row and first column. Let's move down one. Now I want second row, first column. That's going to be in the second row, first column position. I've got 2, a 4, and a 6. You see I've got 2, 4, and 6. 9, 8, 7. 9, 8, and 7. Do you see that going first position, second position, and third position? I multiply them together, then I add them all up. Now let's look at the first row, second column. So the entry here is first row, second column. I want first row, second column. I'm going to take 1, 3, and 5. See, I have 1, 3, and 5. Then we're going to have 6, 5, and 4. 6, 5, and 4. And then we multiply by position, and then we do addition. And that is matrix multiplication. This is a mathematical operation that has a ton of special mathematical properties. It has tons and tons of algebraic properties, geometric properties, you name it. It's got some special features. This is important to us. We are going to be relying on this one operation for the rest of the entire semester. All right, so here A is a 2 by 3, B is a 3 by 2. A 2 by 3 times a 3 by 2 is going to be a 2 by 2 matrix. which we get here. Now, if I switch the order, I've got B times A. B is a 3 by 2. A is a 2 by 3. So it's 3 by 2 times 2 by 3. We're going to have a 3 by 3 matrix, like we have right here. And to get this, let's go through the entire process. Now, one thing you'll notice when I do this by hand, I actually, to help me remember that I'm working by rows on the first one, I underline my rows. To help me remember that I'm working on columns, I put lines between my columns on that one. And that helps me keep it straight, that I know that I need to work with the 9-6 and the 1-2, the 8-5 and the 1-2, the 7-4 and the 1-2, and that gives me these entries. Now, so do you notice that the entries from the first column are in the first column? You see that? That's 1, 1, 1, 2, 2, 2. That's not a coincidence. Now 9 and 6, that's in the first row on the left. I've got 9, 6, 9, 6, 9, 6, and 9, 6. That's not a coincidence. So a way for us to go through and double check to make sure we're doing this right is I go through, I see 3, 3, 3, 4, 4, 4, get the same number every time, that's a 3 and a 4, 5 and 6, 5, 5, 5, 6, 6, 6, okay. And then I already did 9, 6, 8, 5, I know I have 8 and 5, 8 and 5, 8 and 5, 7 and 4, 7 and 4, 7 and 4, 7 and 4. So I can double check to make sure that the entries coming over here are landing where they're supposed to over here. That will help me out. All right, so something that you need to be aware of right off the bat is A times B is a 2 by 2 matrix. B times A is a 3 by 3 matrix. Those don't equal to each other. A times B and B times A are completely different sizes. This means that matrix multiplication is not commutative. That means that A times B does not equal B times A. And that will almost always be the case. There's a couple of special situations like diagonal matrices that it's a special case. We have a commutative property, but in general, nope. All right, now there's a distributed properties of matrices. So if I take parentheses A plus or minus C, multiply by A on the left, I can distribute so it's AB plus or minus AC. If I have A plus or minus B parentheses and I multiply by C on the right, I can go through and I can distribute just like I did with regular numbers. The difference here is I can't switch the order. Like if A is on the left, A has to stay on the left. If C is on the right, C has to stay on the right. If I have A plus B times C plus D, sorry, I'm boring myself. Oh, okay. A plus B times C plus D, I can, once again, I can go through, I can distribute the A plus B parenthesis, boom, I distribute, and then I go through, I distribute the C, I distribute the D, and we get this formula. All right, so now, when we think about multiplication with vectors, vectors are matrices with one column and row vectors are matrices with one row. The rules are the same. The rules do not change. It's just that now I'm indexing with a 1 and that's it. Okay, so let's say that A is n by P, B is P by 1, C is P by 1, and D is n by 1. So here we have a matrix, regular size matrix. We have vector, vector, and we have a row vector. Sorry, no, this is, no, sorry, these three are just vectors. They're just regular vectors. All right, then what's going to happen is if I multiply A times B, so I take the matrix, I multiply by a length P vector, the P's cancel in the dimensions, I get an n by 1 matrix, which is a vector. If I multiply on the left by the transpose of D, notice that D is an n by 1, so the transpose is 1 by n. I multiply, we get 1 by P, a row vector. So if I multiply a matrix by a vector, I get a vector. If I multiply on the left a matrix by a row vector, I get a row vector. Now if I take a vector, transpose, so then it has the form of a 1 by n, and C is, or see, it's 1 by p, then p by 1 is going to be a 1 by 1 matrix. That's better known as a scalar. And then if I multiply D by the transpose of C, it's going to be a P by P matrix. Easy peasy lemon squeezy. Now, if I take a vector and multiply by its transpose on the left, what's going to happen is that's going to be the 2 norm squared. It's going to be the square of the entries, and then I add it up. Now, if I take the vector and multiply by the transpose on the right, then I'm going to get a square matrix. And the 2 norm of a vector is the Euclidean distance of the tip of the vector to the origin, and that is just the transpose of the vector times the vector in square roots, which this is the standard Euclidean formula. Now the J vector always just has 1s. The J matrix just has 1s. So if I take J transpose J, that is n because I've just taken 1 times 1 and then adding them all up. If I take J times J transpose, well, I'm just multiplying a bunch of 1s over and over and over, and we get the J matrix. So notice that lowercase j is a vector, uppercase j is a matrix. Now another formula is that the transpose of B times J is the same as the transpose of J times B, and that is going to be the sum of the entries in the B vector. And so if I use this formula and divide by n, I get the sample mean, right? Nice, nice. All right, so now if A is n by P, and I multiply by the transpose of the J vector, and I multiply it on the left, J transpose A, that's going to be the row sum, this will be the row vector of column sums. So I can get column sums of a matrix by doing this multiplication. And here, if I multiply A by J and J is on the right, then I'm going to get row sums. Okay, so now here's a theorem for us. If A is n by P and B is P by M, then first of all, we can do multiplication. If I do the multiplication, then take the transpose, that's the same as taking transpose of B times the transpose of A. So you notice that it's like I distributed the transpose operator, but I switched the order of the matrices. Okay, how do I get this? How do we prove this? Well, the entries of A times B, using the formula that we've already looked at earlier in the video, this is going to be the sum, k goes from 1 to p, of aik times bkj. So remember, when I do the summation formula, I'm matching the column position to the row position. And then I and j just match here. So I'm adding up over k. Okay, well, when I take the transpose, if you remember the transpose, we switch the row and columns. Rows become columns, columns become rows. Okay, well, if I'm doing that here, if I look at this formula, what's going to happen is I just switch I and j. Rows become columns, columns become rows. Okay, okay. Well, so I took this and I switched it because I know, so remember, C is the transpose of AB. So when I take this, I need to do the transpose. You notice I switch the indices. I switch the indices here, so here it's ij, here it's ji. Transpose operation is switching indices. And then I just rewrite this. So it's ajk, bki. Well, what if I just go ahead and switch the order? Okay, I can do that with multiplication, right? Regular old scalar multiplication, we can switch the order, and I go ahead and do that. Okay, okay. Now consider this. Let's think about for a moment, what is this bad boy over here? Well, if I take, this bad boy, B transpose times A transpose, well, that is the multiplication of taking B transpose and A transpose, all right, all right. Well, when I go ij, I have ik, kj like this, just from the definition of multiplication. Now I know it's a transpose. The transpose means I switch the indices. So then this ik becomes ki. You notice the transpose operator disappears. This kj here becomes jk, and the transpose disappears. All right, well, now I'm going to go ahead and rewrite that because I no longer need the parentheses now that I took care of the operation on the matrix. So now it's bki times ajk, which is exactly what we got up here. Lo and behold, it's a Christmas miracle. All right, so here's a corollary. If A, B, and C have dimensions so that multiplication is defined, then the transpose of A, B, C is equal to C transpose times B transpose times A transpose. So what do we see from this? We see that if I have a transpose on parentheses, I just reverse the order of what's inside for multiplication, and I take the transpose of each. Boom. Easy peasy lemon squeezy. Now the proof, that's homework. Enjoy. All right, there's some other ways to write matrix multiplication. All right, so when we work on our problems, what we want to do, we want to use the notation that is the easiest for the problem we're working on. So sometimes it's going to be one version, like with a lowercase. Sometimes it's going to be easier with the uppercase. And we're going to need to be able to move back and forth freely between different notations. If I can't move freely between different notations, I'm going to be stuck frequently. So understanding the different ways to write the same thing is important because different notations lend themselves to different problems. That's just how theory goes. All right, so let's say that AI transpose are the row vectors of A and BJ are the column vectors of B. Then I can write A as a stack of row vectors. So here we're saying that this is a bunch of row vectors. I should not have that T there. Okay. Well, the troubles with PDFs. All right, and B I can express as a bunch of column vectors next to each other. So here I have row vectors stacked on top of each other. Here I have column vectors standing next to each other like this. So the A I'm representing like in this manner, that this is the first row of entries. This is the second row of entries. Next would be the next third of entries, and so on. Here it's first column, second column, third column, and so on. Well, when I do the multiplication, what's going to happen is that it's just going to be the ith jth entry. I take the ith row and the jth column, and then I just multiply them individually. And that gives me another way to write this out. Sometimes this is easier, sometimes this is harder, depending on the problem that I'm working on. Another way to do this is I can write AB as each of the row vectors multiplying B. And this is in a stacked manner, and will give me the same thing as I have here, and in the other notation will give me the same thing. Or I can write this as A times each of the column vectors of B. Either way, sometimes one is easier than the other depending on the problem I'm working on. Sometimes on a proof, you might actually use multiple notations just to use the easiest one at all times. All right, if A is an N by P matrix, then A transpose A is P by P. It's the product of the columns. It comes from multiplying columns together in that special manner. A times A transpose is N by N, and the entries are the product of the rows. Both of these products are symmetric, and A transpose A is equal to 0 if and only if A is equal to 0. Now multiplication with diagonal matrices, actually let me back up. When we get to eigenvalues and singular value decomposition, so like we do when we're talking about principal component analysis, this A transpose A is going to be super important for us. It's also really important for the theoretical derivation of linear regression, just so you know, which we'll be getting into. Oh, by the way, everything in chapter 2 is important. Everything in chapter 2 is important. Make sure you know chapter 2 of the book. We are going to be relying on it heavily. I'm going to assume you know it. Why? Because the material we'll be going over is sticky enough as it is. If you don't take the time to master chapter 2, you're not going to get the later material. Study chapter 2 until you see it with your eyes closed. Like if you're not proving matrix theorems in your sleep when you close your eyes and you don't dream about proofs, then you're not studying for this class enough. All right, so now multiplication with diagonal entries. If A is an n by p matrix and D is diagonal, n by n, E is diagonal, p by p, and we're going to go ahead and just say that the D's are the diagonal of D and the E's are the diagonal of capital E, then the entries of D times A times E are DI times AIJ times EJ. You notice how the I's match the I and the J matches the J. And in general, most of the time, D times A does not equal A times D. There's a few exceptions, but as a general rule of thumb, no, they don't. Special case is the identity matrix. I times A and A times the identity matrix is always equal to A. Now here we're implying things about the dimensions, but assuming that it's a square matrix, then it'll go along with what I was just talking about. Okay, the next thing we need to talk about is quadratic form. If A is a symmetric matrix and Y is a vector, then Y transpose A times Y is equal to, now this is a special formula, I'm going to take all the AII's, multiply by the YI's squared, add them up. So I go from 1 to n. Now, here, I'm going to take AIJ times YI, and I'm going to multiply these together, and then I'm going to add up all the cases where I does not equal J. Now, if A is n by p, x is n by 1, and y is p by 1. So here we're just saying that x and y have the dimensions that multiplication makes sense. Then this formula of x transpose A times y is going to be this one scalar number of xi times aij. Notice that the i's match, the index match. Aij times yj. Notice that the j's match. And then I add them all up for all of the values. Now, Hadamard product is also called element-wise multiplication. This is where I go through and I just match up entries and multiply them together. This does not have as many special properties as you would think it would. It seems like this would be a more intuitive form of multiplication, but it doesn't have very much bang for its buck. Just letting you know, we're not going to be using this very much. Oh, something I forgot to say is that when we talk about quadratic forms, notice I've got a degree 2 right here. That's why we call it the quadratic. All right, well, that's all I got for you. Take care and goodbye.